Okay, so in last lecture, we studied about the dipole, right? We found out the potential due to dipole. Now, let us see what is the potential energy of a dipole when it is kept in an external electric field. Okay, so let us see this topic first. Potential energy of a dipole in uniform electric field. Suppose there is some uniform electric field in this region. So how do we show uniform electric field? By equidistant parallel lines, right? So suppose there is this uniform electric field in this region and an electric dipole is kept. Okay, electric dipole is kept in this electric field. Okay, so we have this electric dipole kept like this. Okay, so this is negative charge minus q, this is positive charge plus q. So we know, we studied this in electric charges and fields, that this electric field will exert some torque on this dipole, right? So the electric field exerts some torque, okay, because there is a force on this positive charge which is directed like this. Let's use this color. The force on the positive charge is directed like this. Force on the negative charge is directed like this. And these are two equal and opposite forces. They form a couple, right? So this is F plus bar, this is F minus bar. These are two equal and opposite forces. They form a couple. And what is the net result of couple? So couple will rotate the body on which it is acting. Okay, so it acts on this body, right? So it will rotate this body. Okay. Now suppose we want to rotate it against the couple exerted by the electric field. So we need to exert some external torque, right? So how much should be that external torque? It should be equal to the torque due to the electric field, right? So okay, we know the magnitude of torque due to the electric field on dipole. How much is the magnitude? We know it is tau equals to Pe sine theta. Okay, so at least this much torque should be exerted by some external agency in order to rotate it against the electric field, right? So if you rotate it against electric field, then only some energy will be put in the system and it will get stored as the potential energy of the system. Okay, so the external torque needed to rotate the dipole against electric field, against E bar. Against E bar means the torque due to E bar. So that external torque must have at least this much magnitude. Torque external is equal to Pe sine theta. Okay, where P is the dipole moment, Q multiplied by the distance between plus Q and minus Q, that is length of dipole. We write it as 2a. Okay, so P is equal to Q times 2a. E is the electric field, and theta is the angle between this electric field and the dipole moment. Okay, so this is P bar, this is E bar, this angle is theta, right? This angle is theta. This angle is theta. Okay, so now suppose we rotate it by very small angle, let's call it d theta. How much would be the work done? So work done in rotating the dipole through small angle d theta is suppose dw. So it will be what? External torque. Okay. I want to find out work done due to the external torque, work done by the external torque. Okay. Work done by rotating the dipole. Work done by external torque in rotating the dipole to small angle d theta. Okay, that's what I am finding out. So it is external torque multiplied by d theta, that is Pe sine theta multiplied by d theta, right? So this is the small work done when we rotate it through small angle d theta. So what will be the work done in rotating it from some initial angle theta 1 final angle theta 2, or let's say initial angle is theta I for initial, to final angle theta f. Okay, work done for rotation from initial angle theta I to final angle theta f. So it is just integral of this. Okay, so W is equal to integral of dw, which is Pe sine theta d theta. So initial angle is theta I, final angle is theta f. Okay, so P is constant, and we have considered that the electric field is uniform electric field. Okay, so it is also constant. We can take them outside. P and E we can take outside. So it is just integral of sine theta d theta. Initial limit is theta I, final limit is theta f. So what is this integral? It is cos theta or minus cos theta? Okay, it's minus cos theta, right? It's minus cos theta. So W is equal to Pe multiplied by minus cos of theta. The initial limit or lower limit is theta I, upper limit is theta f. So you can take that minus sign outside, and you can write it as Pe multiplied by cos of theta. So then you can substitute the limits. Okay, cos of theta f minus cos of theta I, right? So this is work done. Okay, and this work gets stored as the potential energy of the system. Okay, this work gets stored as the potential energy of the dipole in external electric field. So we can say this work done is equal to final potential energy minus the initial potential energy. So we can say it is final potential energy when the angle between the electric field and dipole moment is theta f, minus the initial potential energy when the angle between electric field and dipole moment is theta I, right? So this is what we get. Okay, this is what we can find out, and we can see it. Okay, we are seeing this again and again. Which thing we can actually calculate is the change in change in potential energy only, and not the actual potential energy. We cannot find out the actual value of potential energy, right? So what we do is we choose some reference point where the potential energy is zero. Okay, the reference point where the potential energy is zero. So here we'll consider a reference point, okay, or reference initial condition we can say. So just like when we bring some charge from infinity and keep it at some distance, okay, away from some other charge, the reference point is infinity. So here the reference point is angle, initial angle equal to pi by 2, or initial angle equals to 90 degrees. Okay, so very often we choose this reference point. Why? Because cos of this is 0. Okay, and we can say that the initial potential energy is 0. Okay, so see, we can write this as, okay, so we choose this reference point theta equals to pi by 2, where u of pi by 2 we set it as equal to 0. Okay, so this is our initial angle. Okay, so theta I is equal to pi by 2, and now final angle theta f can be anything, can be any theta. Okay, so let's suppose theta f is just equal to theta, right? So we can substitute these values. So what do we get? So we are setting that potential energy at the initial point or initial angle, which is equal to what? Pi by 2. That potential energy is equal to 0. Okay, and then we are finding out potential energy at a particular point. So we get u at particular theta is equal to minus p multiplied by e multiplied by cos of theta minus cos of pi by 2, and we know cos of pi by 2 is 0. Okay, that's why we have chosen, okay, this thing. Okay, initial angle equal to theta. So we get minus p into e multiplied by cos of theta. This is u at a particular angle theta. Okay, that is potential energy of a dipole when it is aligned at an angle theta with the external electric field. So this is dipole moment, the magnitude of dipole moment. This is magnitude of the electric field, and we have cos of theta, where theta is the angle between dipole moment and electric field. So what is this? This thing is dot product, right? We can write this. We can write this as p bar dot e bar. This is the dot product. Okay, so u of theta is equal to minus of p cos theta, we can say, or it is equal to minus of p bar dot e bar. So this is an expression for potential energy of a dipole in an external electric field. After that, next we'll talk about the equipotential surfaces. Okay, so next we'll talk about the equipotential surfaces. So what is an equipotential surface? The meaning is clear from the name itself, right? What is an equipotential surface? The put sorry, the equipotential surface is a surface where the potential is equal, okay, at all points of the surface, right? What is an equipotential surface? It's a surface for which potential is equal at all points of that surface. Okay, so the surface I'm sorry, for which the surface for which electric potential is equal at all points of it, okay, of the surface, is known as an equipotential surface, right? So we'll see some examples of equipotential surfaces, and then we'll talk about the significance of equipotential surface. Okay, so let's first of all let's consider a point charge. Okay, so this is charge plus q, capital Q. So how does the equipotential surface due to this point charge look like? So point charge is suppose at the center. This is the point charge. So it will be a spherical surface, right? Because potential due to point charge, we know potential due to point charge at distance r away from it, it is given by V equals to 1 upon 4 pi epsilon naught multiplied by Q upon R. Okay, this is formula for the potential due to point charge. So it means that you take any point at distance r away from the point charge, the potential at all such points will be what? It will be equal. Okay, potential at all such points will be equal, right? So if you collect all such points, what will you get? You will get a sphere. Yes, no? Okay. So how does an equipotential surface due to a point charge look like? It, it's a sphere. Okay. Then if you want to draw another equipotential surface, then draw another sphere. Okay. Draw another sphere which is concentric to the sphere, which is concentric to the first sphere. Okay. Then this is another, I can say, equipotential surface. Okay, so equipotential surfaces due to point charge are concentric spheres. Okay, and what is the center of those spheres? So center of those spheres is location of the point charge. Okay, now can you tell me what is the angle between the equipotential surface and electric field lines? What is the angle between equipotential surface and electric field lines? You can check it here. Okay, so for that purpose only, I have drawn these electric field lines. So electric field lines due to a point charge, positive charge, they are radially outwards. Okay, they are radially outwards. And equipotential surface due to a point charge is a sphere, right? So equipotential surfaces are concentric spheres. Okay, so what is an angle between surface of sphere and radius? So you can see it here, it's 90 degrees. What is an angle between surface of a sphere and radius or radial line? So this angle is 90 degrees. You can see it anywhere, here also. Okay, so it is 90 degrees. Okay, so this is actually a general property. This is not a specific case. Okay, this is not a specific case. This is a general property that the angle between an equipotential surface and electric field lines is 90 degrees. Got it? So this is one property of an equipotential surface. We'll collect them at the end. Now, if we consider two equipotential surfaces, so let's consider this surface and this surface. So potential at this surface and at this surface, it is different. Okay. So now at which surface the potential is more? The surface which is closer to the point charge. Okay, because the formula for potential is 1 upon 4 pi epsilon naught q upon r. So the potential is more for the surface which is closer to the point charge, and it is less at a surface which is away from point charge, comparatively away from point charge. Okay, so now you can see electric field lines flow from higher potential to lower potential. They are perpendicular to equipotential surfaces. This is one property. Next is they flow from higher potential. See this. If you think about this surface and this surface. So let's call them A and B. So this is suppose A, this is B. This point is A, this point is B. So electric field line is flowing like this. The electric field is flowing like this. Okay. So electric field lines flow from higher potential to lower potential. So this is another property. After that, okay, so this is an equipotential surface. This is an equipotential surface for a point charge. Next, let's see equipotential surface for some uniform electric field. This is suppose some uniform electric field, and I want to find out an equipotential surface for this uniform electric field. So this uniform electric field is directed like this. This is E bar. It's directed like this. So how will you draw equipotential surface for uniform electric field? So we just saw that this equipotential surface is perpendicular to the electric field lines, right? So that means if you draw a plane perpendicular to these electric field lines, it will be an equipotential surface for this electric field. Okay, so let's draw a plane like this. Now this is 3D diagram drawn on 2D paper. So it's kind of hard to imagine that this will be perpendicular to the electric field. But let's imagine that it is perpendicular to electric field. Okay, so this plane and these electric field lines, they are perpendicular to each other. Okay, so this is an equipotential surface. If you want another equipotential surface, draw another plane parallel to this plane. Okay, so if you think about two equipotential surfaces, they are parallel to each other and they are perpendicular to the electric field lines. Okay, so now is the potential equal at this surface and this surface, or is there some potential difference between these two surfaces? Is potential, let's call them A and B. So is the potential on A and potential on B equal, or is the potential of B, okay, so okay, options, is VA equal to VB, is VA greater than VB, or is VB greater than VA? Tell me. Okay, electric field lines flow from higher potential to lower potential, right? So that means electric field lines are flowing like this. They are flowing from A to B, no? So that means potential at A must be greater than potential at B. So what is the answer? Potential at A is greater than potential at B. Option B. Yes, no. Okay. All right. So the equipotential surface for uniform electric field, it looks like this. Okay. So then, okay. So this is equipotential surface of due to uniform electric field. Now, can you tell me which kind of charge configuration produces this kind of electric field? Can you guess it? Or have you seen such a charge configuration? Okay, it's simple. Charged infinite, okay, infinite charged plane sheet. Okay, a charged plane sheet of infinite dimensions, right? So we had seen this. If you have charged plane sheet which is very big, okay, very big, then electric field lines are parallel. Electric field lines are, sorry, perpendicular to the plane of that plane sheet. Okay, so if you have charged plane sheet which is very big, practically infinite, then the electric field lines are perpendicular to the plane of that charged plane sheet. So this kind of electric field is produced by what? A charged plane sheet, infinite charged plane sheet, right? So these are equipotential surfaces for infinite charge plane sheet. Okay, then we can consider an example of a wire. Okay, let's consider an infinitely long straight charged wire like this. So now, if this is that wire, then electric field lines are directed outwards. Okay, they are perpendicular to length of the wire, so they are directed in all possible directions. Okay, um, perpendicular to length of the wire, right? So electric field lines due to this wire are perpendicular to its plane. Oh. Right. So this wire is positively charged. Infinitely long, straight, positively charged wire we have. So how will the equipotential surface due to this wire look like? So we know electric field lines are directed. They are directed like this. If you consider this side, they are directed like this. These are electric field lines. Okay, if you consider this direction, they are directed like this. Right? Perpendicular to length of the wire. And that's why the equipotential surface for this wire will be a cylinder. Okay, it will be a cylinder. Because if you consider a cylinder, then these electric field lines will cut perpendicular to the curved surface of the cylinder everywhere. Okay, so equipotential surface due to a wire is a coaxial cylinder. What does it mean by coaxial? Having same axis as that of the wire, because wire is also cylindrical. So this is an equipotential surface. Right. So given a charge, sorry, given a charge configuration, we should be able to identify the equipotential surface. Okay. So if we are not able to memorize, we need to memorize this thing, this property, that equipotential surface is always perpendicular to the electric field lines. Got it? Yes, no? Okay. And then let's talk about another property, actually very important property of an equipotential surface. I'm sorry. So let's suppose this is some equipotential surface. This is some equipotential surface, and I want to move some charge. This is suppose some charge, small q, which is at location A, and I want to move it from location A to some location B. Both points belong to the equipotential surface. Now, how much would be the work done in this process? How much would be the work done? Work done would be zero, right? Because potential at this point and potential at this point is equal. So work done would be zero. Okay. So I can say since VA equals to VB, therefore work done to move a charge, work done to move charge small q from A to B, from A to B is equal to 0. Okay, because work done is equal to what? Potential difference multiplied by the charge. Okay, work done is equal to potential difference multiplied by the charge. Therefore, the work done must be equal to 0. All right. So we have discussed all important properties. Let us just write them down so that we remember them. Let us just recall the properties of an equipotential surface. Properties of equipotential surfaces. So first one is very obvious, that potential at all points of equipotential surface is 0. Okay, so potential at all points of equipotential surface is 0. Then second property is electric field lines. Electric field lines are perpendicular to equipotential potential sorry potential surface. Oh, surface. Okay. Next property, the electric field lines, they move from higher potential to lower potential. Okay, so electric field lines are directed from equipotential surface having higher potential. Okay, so last statement, equipotential surface having higher potential to equipotential surface having lower potential, right? Next property is work done to move a charge on equipotential surface is 0. Work done to move a charge on an equipotential surface is 0. Okay, so these are the properties of an equipotential surface. Any doubt in this? Okay, so let me just check whether I have mentioned all properties. Yeah, I guess so. All right. So then we'll see the relation between an electric field and equipotential surface. Okay, I mean, we have already discussed the relation between electric field and equipotential surface. Okay, so we'll find out an expression for electric field in terms of the potential. Okay, using equipotential surfaces. So let us see the relation between electric field and equipotential surfaces, or we can say electric potential, relation between electric field and electric potential. So see, let's suppose that this one, sorry, not this one. Let's suppose that this surface and this surface, these are two equipotential surfaces. Let's call them A and B. These are equipotential surfaces. Okay. So potential at this surface is VA, potential on this surface is VB. So we know the electric field will be directed perpendicular to these surfaces. So if we consider any one electric field line will be directed like this. Okay. This is the direction of electric field at these points, we can say. Right, this is E bar. Now, see, this is the direction of electric field. Okay. This potential of this surface is suppose VA, potential at this surface is suppose VB. So now how much would be the work done against the electric field if you move some charge from A to B or B to A? It will be force due to the electric field, okay, multiplied by the charge, right? See, what will be work done against the electric field to move some charge, to move some charge small q from surface B to surface A, B to A. How much would be the work done? Let's call it delta W is suppose work done, or we can say WAB is the work done. Okay. So it is equal to what? It is final potential, which is VA minus initial potential VB multiplied by the charge, right? So we get this formula for work done using potential difference. Okay. So work done is equal to what? Potential difference multiplied by charge. Okay. Final potential minus initial potential multiplied by charge. Then work done is also equal to the force multiplied by displacement, right? So let's suppose the charge is moved from here to here. So this is the initial position, this is final position. So the displacement between these 2 points is the perpendicular distance. It's the perpendicular distance between these two surfaces, A and B. Okay, so let's call it dr. Okay, and electric field is directed like this. So force due to electric field will be directed like this. So if we want to move this charge from B to A, from surface B to A, we have to exert some external force against the electric field. Okay, so suppose F external is equal to the external force. It is the external force that we apply to do work against the electric field. So how much would be its magnitude? So magnitude will be equal to what? Force due to the electric field. Okay, so it is Q into E. This much is magnitude, right? So therefore, work against electric field. Okay, work against electric field is WAB. So it is equal to minus of, okay, force due to electric field, which is Q into E multiplied by minus of QE multiplied by the displacement, right? Or I can say, okay, now external force will be what? I have considered magnitude only. If I consider direction also, F external will be equal to what? Minus of Q into E bar, right? Okay, it is directed opposite to that of the electric field. Okay, so how much would be work done? Work done is minus of QE which is external force. Okay, F external multiplied by displacement dr. It is minus of QE into dr. But we found this formula for the work done. Okay, so work done is equal to VA minus VB multiplied by charge. So we can substitute that here. So it is VA minus VB multiplied by the charge. And we can cancel out the charge. So then if we cancel out the charge and move dr on other side, what do we get? We get E is equal to minus of VA minus VB divided by dr. Okay, it is equal to minus of difference in potential with respect to the distance, right? And I can say that VA minus VB, since it is difference in potential, so I can write it as dV. dV is equal to VA minus VB. Okay, so therefore I get electric field is equal to minus of dV by dr. So I get this formula for the electric field. So what is electric field? It is minus of the gradient of potential with respect to position or distance. Got it? Yes, no? Okay. So this is known as, so electric field in some region is negative of gradient of potential with respect to the position. Okay. So for an example, if I consider electric field in x direction, okay, if I consider electric field in x direction, okay, in some region, let's suppose in this region, the electric field is directed only along x direction, right? So for this region, I have to take change in potential with respect to the x axis only, right? If I want to find out the electric field, let's suppose I know potential at A, I know potential at B. So the distance between them is dx, okay? And what is dv? So dv is equal to Va minus Vb, okay? So electric field is equal to what? Minus of dv by dx for one dimensional, okay, one dimensional problem, or the electric field if it is directed along only one axis, right? Then we can find it using this formula. Yes, no? Okay, but this will be true for this problem, okay, where the electric field is directed along x-axis only. So in general, electric field is a vector quantity. That means it will have three components. Okay, so electric field will have three components. So in general, how do we find the electric field given potential? So for that, we'll have to find out three components of electric field separately. Okay, so I will write it down and then explain. Okay, so electric field, electric field in three dimensions is given by this formula. E bar is equal to minus of, sorry, E bar is equal to minus of derivative of potential with respect to x, and here potential will be function of xyz coordinates. Okay, and I'm writing different sign, different symbol for the derivative, okay, which is known as partial derivative. Okay, so this will give me x component. Okay, this will just give me x component. So this thing multiplied by I cap. This is the x component of electric field. Plus there will be y component. So derivative of potential. This is known as partial derivative. So partial derivative of potential, which is function of x, y, z with respect to y. Okay, multiplied by j cap. Plus partial derivative of potential, which is function of x, y, z with respect to z, multiplied by k cap. Okay, so this is how we will find out the electric field in 3 dimensions, given potential in 3 dimensions. Okay, potential is scalar quantity, electric field is a vector quantity, right? So now see, here potential will be function of x, y, z, or we can take an example. For an example, potential v of x, y, z is equal to suppose x, y, z. Okay, so when I take derivative with respect to x, I will treat y and z as constant. When I take derivative with respect to y, I will treat x and y as constant. And when I take derivative with respect to z, when I take derivative with respect to y, I will treat x and z as constant. And when I take derivative with respect to z, I will treat x and y as constant. That is the meaning of partial derivative. Okay, partial means we consider, see, we are taking derivative with respect to x. Okay, then we'll consider x part of this function only. Okay, and we'll treat terms having y and z as constants. Okay, so this can be anything. This can be, for an example, v is equal to x multiplied by sine y. Okay, e raised to z, whatever. So terms containing y and z, we'll consider them as constants. Okay, so this is the meaning of partial derivatives. So this is read as, okay, so different people read it differently. So dou v by dou x, this symbol curly d, you can say, this is called as dou, or you can just call it partial. Okay, so you can call it partial v partial x, or you can call it partial derivative of v with respect to x. And we have a short form, okay, short symbol to write down this formula. We have a short symbol to write down this formula. I'm sorry. So in short, we write it like this: E bar is equal to minus of del V. Okay, that's it. Right. So this is known as the del operator. Okay. This curly D, some people call this curly D as del also. Okay. So this is known as del operator. Okay. And what is meaning of this operator? So this is equal to, del operator is equal to I cap multiplied by del by del x, or dou by dou x. Okay, plus j cap multiplied by dou by dou y, plus k cap multiplied by dou by dou z. Okay, this is meaning of del operator. All right, so let us see an example. Okay, let us see an example of this. Okay, let's consider this potential only. V of xyz is equal to xyz, and calculate the electric field. Okay, so suppose the potential in some region is given by, V of xyz is equal to xyz only. Okay, find the electric field. So what is electric field in that region? Okay, so we have got this formula for the electric field, right? So E bar is equal to what? E bar is equal to minus of dou V by dou x multiplied by I cap plus dou V by dou y multiplied by j cap plus dou V by dou z multiplied by k cap. So I'm not writing explicitly that V is function of xyz. It is function of xyz. So that means it is equal to minus of, okay, dou by dou x of what? xyz multiplied by I cap plus dou by dou y of xyz multiplied by j cap plus you have dou by dou z of xyz multiplied by k cap. Okay, and then as I have explained, when we take partial derivative with respect to x, so I'm taking partial derivative of this term with respect to x. So all of these are variables, right? X, y, z, all of these are variables. But since I'm taking partial derivative with respect to x, I will treat y and z as constants. So if they are constants, so if they are constants, I can take them outside of the bracket, outside of the derivative. Okay, so I can write it as minus of y multiplied by z multiplied by derivative, partial derivative of x with respect to x. Okay, and we know derivative of x with respect to x is 1, right? So this is simple way. Okay, this is the simple trick to take partial derivatives. Okay, not a trick, partial derivatives are taken in this way only. So instead of y and z, if you had suppose y raised to 2 or y raised to 5, you can take all that outside of the derivative because it's a constant when you are taking derivative with respect to x only. Okay, so what we do is we treat them independent of each other, right? Then plus you have derivative of xyz with respect to y, partial derivative. So here you will treat y or function of y only as a variable, and you will take everything else outside. It is x times z multiplied by del y of y, okay, multiplied by j cap plus when you take derivative with respect to z, you will take x and y outside. So del by del z or dou by dou z of z multiplied by k cap, and this is equal to, okay, this is equal to what? Yz into I cap, okay, because derivative of x with respect to x is 1. So this is equal to minus of yz multiplied by I cap plus xz multiplied by j cap plus xy multiplied by k cap. So this is the formula for electric field in that region. Okay, and then maybe a question can be like this: what is electric field? Okay, what is electric field at some point? Let's suppose 1 1 1. Okay, what will be electric field at this point? At this point. So first of all, we'll find out this formula and we'll put the values of x, y, z. Okay, the values of coordinates. So coordinates are 1 1 1. Okay, for an example. So it will be what? 1 multiplied by 1 into I cap plus 1 multiplied by 1 into j cap, 1 multiplied by 1 into k cap. So electric field will be what? So at 1 1 1, electric field is equal to minus of x cap plus y cap plus k cap. Okay, so this is just a simple example. E bar is equal to minus of x cap plus y cap plus k cap. Got it?